Okay, hello and welcome to my channel. Today we're gonna be talking about the resonance um, and quasi-bound state again. This time we're gonna look at an example, sort of an exercise, and we're gonna solve it together. And beforehand, I want to sorry because it's pretty loud outside. I don't know if you can hear it, but for me it is like very loud. The karaoke from like the neighbors. All right, so get that. Let's begin. So you might remember like that one time I made an example about the quasi-bound state when you have something like this and the energy is over here. So I think the old example is something like this. And when you have your energy over here, you can produce something called a quasi-bound state when your energy is matched with an energy eigenstate of the imaginary infinite square wave potential that you slapped on here. So that would allow for tunneling, even so, meaning that your wave can pass through this hump, even though your energy is obviously not supposed to do that. So today we're going to take a look at something more square, more uniform. So your infinite wall, here is your potential part 1. This is your next part with the potential. There we go. So we're gonna, this part is obviously gonna be the K. So this is a kappa. It's a K prime. And over here is our K. Okay, so this would have a value of minus V naught. So with something like this, let's write our wave function. Okay, so for this is A, this is 2A. Okay, so for 0 to A, 0 to A, and A to 2A, and outside of 2A. So first, take a look at our region 1. We call this region 1, region 2, and region 3. Let's take a look at our region 1. It would vanishes at 0. Therefore, our wave function would have the sine part. So this would be A sine K prime A. We use the K corresponding to our region. Next one is our region 2. And this region is obviously, okay, I forgot to write our energy. Okay, no, my pen died. Our energy would be greater than 0 and less than our V1. Call this V1. Right. Okay, so that would be our energy. So it would be somewhere here, meaning that our region 2 would be a decay function. So decay meaning that it would be some form of cosh and sinh. And to write this, it would be C cosh kappa A plus D sinh kappa A. All right. Next is the outside. As I said in the last video, outside is universal for these kind of problem. That would be EI delta sine kx minus plus, I'm sorry, that would be a plus, not minus. Right, so this is your wave function, and your Schrodinger equation would be minus plus minus accordingly, since this guy is minus kappa x, so you throw it over, that would be just real quick, would be the second derivative would be equal to just kappa squared psi. Unlike the normal, I will take the region out here is minus k squared. Right, just some quick fun facts. Right, so once you write your wave function, now let's take a look at the boundary condition and continuity. Okay, so first let's take the continuity at A first. Continuity at the x equal to A. X equal to A. Okay, this is x. Sorry. X, alright. So at x, that would be the continuity of your wave function and their derivative. That would mean that A sine k prime A equal to c cos kappa A plus d sinh kappa A. And you see immediately we cannot solve this, since there wouldn't be any term that we can cancel, and therefore we can't really find our constant here. And now it is time to remember one crucial thing about these problems, is that the inside here, these wave functions, you can pick them yourself. Well, exclude this one because it is universal for these kind of problems, but the other two, you are free to pick them. And now we're gonna pick the middle one, the region 2 wave function. And you see what would make these vanishes at first would be moving the point of origin, here is x, or 0, you're gonna move it to A. So that, well, when you take the continuity at A, that would be A minus A equals 0. That would give you something here. And when you take it is take it as 2A, and that would give you A. So mainly you just want this part, as it will give you something to start with. Otherwise you would be stuck. So we're gonna rewrite this entire thing as kappa x minus A and d sinh kappa x minus A. Alright, so that would give you 0 and 0, or 0 and sinh 0. Sinh 0, this term is 0, therefore this term is 1. So from here you get that your c is equal to A sine k prime A. There you go. That is your first part. Now we take the derivative. Derivative would be k prime A cos cosine to c. Okay, I will just write c. You use that. C sinh kappa x minus A minus A sinh 0 plus d cos 0. From here, get your d to equal to ak prime cos k prime A, and divide it by kappa, kappa and kappa. Forgot that part. All right, so now you got your C, and D. Now we're going to take the continuity at 2a. So maybe I can erase this part. I'll wait for like 5 seconds. Right. So next is the continuity at 2a. So that would be our region 2 and 3. So first one is, that is a, no, it's a sine k prime a cos a, yeah, a plus a k prime kappa cos k prime a sin kappa a. This guy is equal to the region 3, which is this guy. Okay. This one we can't really cancel anything, so we're gonna move on and take a look at its derivative, which is you take the kappa out. Inside is sine k prime a sin kappa a plus this, the d cos kappa a. This guy would equal to kei delta sine ka plus delta. Right, now you divide. Right, up. This is cos, I'm sorry. Cosine, not cos. You divide, and what you get is k. No, you divide the k. So k one side, that would be k cotangent. This is 2a, so it's 2ka plus delta. That would equal to kappa. The a, we just ignore the a. Divide this up, which is sin kappa a plus k prime over kappa cos k prime a cos kappa a divided by sine k prime a cos kappa a plus k prime over kappa cosine k prime a sin kappa a. Right? So you have this, and we want to work with the tangent here instead of cotangent. So what we would do is we flip this entire thing, we bring this guy over here and flip the entire thing. So when we flip it, what you get in the end is from here. I'm gonna write it up here, and my pen is dying. Tangent to ka plus delta k over kappa, and you flip the entire thing. Sine that is cos sin kappa k over kappa. These sinh kappa A, cos kappa A. This is your final solution. And from here, you can solve your things to get your delta, to get all sorts of stuff. And here you can actually, well, recognize that there are like Ka and stuff. So that means you can put these into unitary numbers. I don't know if my pen can hold up till the end of this video, but I'll try my best. Okay, so we're gonna assign here, and later we're gonna draw the plot over there. So we have our Ka, we assign that to be equal to U. Next is the Z naught square, 2mv naught A square over H bar square. Z1, since we have, well, two different potential value, V1A square over H bar square. Okay, what we have next would be your dimensionless energy, E over V, and here V we take V1. E is, H bar square K square over 2m V1. And you see, this can almost, you can almost get your Z1 square with this. So we're just gonna time A square on both the numerator and denominator. That would give you, I believe, U square. Yeah, U square over Z1 square. Okay, this, I don't know if we have enough space over there. So what you get in the end is you have your K prime A square and your kappa A square. These would equal to U square plus Z naught square and Z1 square minus U square, respectively. Okay, so with these, we can finally draw our plot and see the physical property of the system or your resonance states. Okay, so first plot is plot of your delta. Okay, I think it won't be able to hold for any longer. Next is your internal wave. Wait, I should. Yeah, what? I shouldn't have erased that part. Nah, whatever. Next is your internal wave. It's AS. Your probability. And finally is your time delay. Time delay. R here is 2A. I just write 2A. D delta dk. Right, so how would these plot looks like and what would they interpret? So first things first is our delta. So this would be our plot of these function and u. So u, plot of u, and we take a specific value, say come up with something, star, U star, no, it's star. So at value star, at star 3 at star. So this is like a specific value, like for example, like alpha, beta. I'll use star here. Okay, so what your delta would look like is that it will come down. At first, it will come down, and to the point around. Okay, so I will draw. As it will come down, and to this point, pi minus pi. So to the point that is around minus pi, it's gonna jump. It's gonna jump up. It's gonna jump up. So that would be the point of. So the point here is where it hits minus pi over 2. It hits pi over 2. That means that it. So the easiest way for you to spot resonance is when your wave here would your phase here would be jumping up a value of around approximately pi. So as we increase the energy, the phase is gonna dip to around pi, then it's gonna jump up. So that would be the sign for resonance. And next is your internal wave amplitude. It's gonna go something like this. And to the point of star, it's gonna jump. Something like that. So at resonance, there is gonna be something inside here as drawn. So here, when the energy is too small, meaning that it still cannot penetrate this, but to one point where it resonates, the wave would be able to penetrate this wall and get inside here. So that's why you can measure something inside there. And for the probability density, or just probability, that would be characterized by the two humps, meaning that at this point it dipped down and something appeared inside, so it is detected. Right, next is our time delay. Our time delay would actually start from below 0. Would go something like this, up till it hits near the point star. It's gonna jump. Right, and why this happened is that in this period where it is below 0, meaning that your time delay is not 0, because well, your time delay would measure when your wave hit this wall and then bounces off. But here you have this wall instead, so it would bounces off this wall and would go back, and therefore resulted in this negative period. Next is this part where resonance happened. Your wave would be able to leak inside and would linger here for a little bit before it gonna bounce back. Therefore, explain the jump in time delay as we increase the energy, because U is Ka and K is, well, basically energy, as energy is h bar squared k squared over 2m. So I hope that would explain it a little bit. Well, me personally, when I first learned about these plots, it's actually pretty difficult for me, at least. So I hope that I made it clear. You maybe if you have some questions, you can ask me in the comments. And that would be it for today. Goodbye.